It's Paul with the second of the Math156 scripts on linear regression. And now what we're going to try to do is to estimate confidence intervals for the regression parameters. There are two different ways of doing this. The classic one is to do all sorts of statistical tests involving student t-distributions and even f-distributions, which we're not really discussing in this course. And these approaches yield lots of numbers, but they're all based on the assumption of independent residuals with equal variances, probably not satisfied in practice. A second approach is to use resampling techniques using the Bootstrap, and in that case we're making no assumptions about the data. I kind of like that better, so I'm going to go lightly over the first approach. Okay. Nonetheless, the first approach is covered in detail in section 9.5 of the textbook, and you should at least read that section before proceeding, even if you don't take the time to understand the details of all the theorems that are proved. Okay, you've read section 9.5, right? And we can get going. So we're going to load data from the Winter Olympics in 2010. And what we've got for skaters is just for each skater the score in the short program, the score in the free program, and the total of the two. And the question is the score in the short program a good predictor of the score in the free program? Well, first approach is let's plot one against the other, and you're experienced enough now to spot correlated variables. These are correlated. How correlated? Correlation of 0.83, which is pretty high. What about a regression line? Well, we'll just use the LM function in R, saying we want linear regression of free against short, and we ask for summary, and we get more than we ever wanted. If you want to find out what all these things mean, you can look at the R documentation, or you can start out by looking at page 273 of the textbook, where the result of this summary is put in a little box, and a fair amount of it is explained. If you look under coefficients, you can find the two numbers we're most interested in, namely the intercept and the slope, and there's our regression line plotted. But now you'll notice that we're getting standard errors. Now you say, how on earth can there be a standard error for the slope of the regression line? That's just a number that I calculated. It's not a random variable. Well, here's where the maximum likelihood approach starts to pay off. With the maximum likelihood model, these residuals are generated as random variables. And furthermore, we get an estimate of the variance for the residuals. So we can now ask, suppose we use this process to generate the variables over and over again. Each time we'll get different residuals, we'll get a different parameter beta, and therefore it makes sense to talk about the variance of the estimator beta hat of the slope of the regression line, and that is calculated as 0.24. What that means is if you generated different skating scores for the long program according to this model, you would get different regression lines with different slopes, and the standard error of those, which is actually an unbiased estimate of the variance. The book explains you have to divide by n minus 2 instead of by n in order to get that. You get the standard error of this beta. You can also use student t theory to calculate a confidence interval for the beta. We end up with a student t distribution because we are estimating the variance of the residuals from the data. Whenever you do that, you end up with a t-distribution rather than a normal distribution. We had 24 skaters, but we estimated 2 parameters, so we only got 22 degrees of freedom left. There is student T with 22 degrees of freedom. There are vertical lines at the position of the 2.5% and 97.5% quantiles. And in order to get a t confidence interval, we have to use the standard error as a multiplier on these quantiles, and then add in our estimate of beta, which was 1.747 for the middle of the confidence interval, and we say we're 95% confident that the true value of beta lies in between 1.24 and 2.24. A remarkably broad interval, and you look at these regression lines and you say, ha, we've nailed it. We've got exactly the slope of the regression line. And this is a slightly sobering result. It says, not so. Based on our model for what's going on, we could have got quite a different range of numbers. You can also predict the expected free score for a skater with a given short score. And if you try to calculate a confidence interval for this score, things get so complicated that my advice is just ignore it. I'll show you another way of doing this shortly, because all of these calculations are assuming that the residuals are independent, and furthermore, that they're normally distributed. Probably not assumptions that are satisfied in practice. However, for future reference, when we do this a different way, you'll want to notice that the correlation came out to be 0.83. Now let's take a bootstrap view of the same sort of analysis. How are we going to bootstrap these skater data? Well, the way we bootstrap anything. We're going to sample, but we're going to sample with replacement. So we will choose 24 pairs of scores, but because we're sampling with replacement, when we look at what we've got from generating 24 indices at random, there will be omissions, there will be repetitions. So you see that Stefan Lindemann's score was used twice. Florent Amodio's score was used 3 times, and therefore there must have been some of these 24 skaters that didn't show up at all. So now we've got a different result of a different set of skating results, and we can analyze it in the usual way. And when we do that, this time we get a slope of 1.921 for the regression line. If I go back and repeat the process, now I get a different set of 24 skating results. I analyze that. This time I got a regression line of 1.545. So now you see how the bootstrap approach is going to work. We're going to do this over and over and over, and the range of different results we get for the regression line will indicate how much we might be off from the true value. We can also very easily calculate a correlation. In this case, for a bootstrap sample, we got a correlation of 0.94, and that just meant we happened to pick a selection of skaters that gave much more highly correlated results than what we get when we use each skater once. Again, you can resample by hand. Let's do one more. This time we got a correlation of 0.79. So now that we understand how our procedure is working, we'll have the computer do it 5,000 times, and for each attempt we will calculate a correlation, an alpha, a beta, and an expected score for someone with a short program score of 60. So here we go. And now we sit and wait till the red circle disappears in the lower left pane, because this is quite a time-consuming computation. It's done. Good thing I wasn't using my laptop. And we can start looking at the distribution. For example, we can look at the histogram of correlations we generate. If you have your textbook at hand, look at figure 9.17a. It won't be exactly the same, but it will closely resemble this. We can also do a Bootstrap percentile confidence interval, and out of that we'll say we're 95% confident that the true correlation is somewhere between 0.69 and 0.92. We can do the same thing for beta and say we are 95% confident that the true slope of the regression line is somewhere in between 1.37 and 2.15. We can even do something that was very difficult to do with the student T approach and say we're 95% confident that someone who scored 60 on the short program would have scored between 102 and 120 on the long program. Finally, we can draw some of these regression lines. There in heavy black is the regression line for the actual data, and here in red are 50 regression lines for the bootstrapped data. And you can say any of these is a plausible candidate for the regression line also. That gives us a good idea of how much we can trust the single black regression line we calculated. Of course, if we take the mean of those, we're going to get 1.74. You can never make a silk purse out of a sow's ear. You can never get a more accurate estimate of the mean by bootstrapping. Let's finish up by doing one more resampling approach. Now here what we want to assess is the hypothesis that these data really are correlated, that a higher short score leads in general to a higher free program score, and we can test that by permuting one of the variables. The book chose to permute the x values. I kind of prefer permuting the y values, though it works the same either way. And of course, after we permute the data, after we scramble the long program scores, there's no reason whatever for high long free program scores to go along with high short program scores. And sure enough, if we do our permutation, get some permuted free scores, and plot the permuted free scores against the actual short program scores, there's no evidence of correlation. And when we compute the beta for the linear regression, we find we actually have a slope of minus 0.33. Because we permuted things, this number is as likely to be negative as positive. And now we do the usual permutation test thing. We do this many times. I'll do it 5,000 times. And ask, could we, with permuted scores, have got a slope of the regression line that was as large as what we observed? So, permute. Wait a while for things to finish up. And when the calculation is done, plot a histogram of the betas. And you can see that with the scores permuted, we can get slopes of the regression line pretty much anywhere between -1 and +1, but what we saw was 1.737. The probability that that would arise by chance is very nearly 0. Similarly, we can make a histogram of the correlations. We can get correlations between -0.5 and +0.5 by scrambling the long program scores, but there's no way we're going to get the observed 0.83. This form of analysis is something that you might well have a lot of fun with on your final project, and that's what I have to say about it.